Yeah, at first we'll take up the lowest energy, what we call low energy gamma astronomy. And as I told you, this is that typically satellites, and this is essentially because these are very low energy particles and they die in the atmosphere very fast. So you got to take the instrument up. Now the latest satellite is called Furby, and you know probably know Furby was the greatest species of last 100 years, and actually its another name is GLAST. And what you can see is the process pair production here. The gamma ray comes and two electrons and positrons are produced here, and the experiment detection. As I say, it's a typical high energy physics type of thing. Now this is the earlier satellite called CGRO or Cooperative Gamma Ray, and the method is same. It's just that with the technology, one can make the better and better instruments. Now, one of the most important things which came out of the gamma ray, the Compton gamma ray, was what we call gamma ray bursts. And I noticed that it has been discussed earlier, but what I just want to touch upon it because anything at gamma ray astronomy will not be complete without that. And what they are essentially gamma ray bursts can release more energy in 10 seconds than the sun will emit its entire billion, 10 billion year lifetime. And it occurs once in a few billion years in the galaxy. And what's most important is they are the most powerful explosions of energy in the cosmos since the Big Bang itself. Now there are several things about it. Oops. But what I would like to point out is not the properties of this, which are actually very interesting themselves, but the thing is what is responsible for it, which is the physics of it. The short means the time scale by that short few seconds type of gamma ray burst. It looks like they could be from neutron star. It's very fascinating thing. Two neutron stars come together, and when they merge, you get a flash of gamma rays. You know, it's brilliant. If you could see it gamma ray by itself, you would see it. You would be blinded by that type of a thing. And it would be in globular clusters, which you probably know are the oldest stars. Essentially, what you want is a space where lots of stars are together. So globular cluster is ideal. Another thing is what's called the longer GRBs, which is the little larger time scale, is a hypernova. I mean, the hypernova, there's nothing great in the sense that it's just very great, like supernova is supernova, but hyper is something much bigger than that. It is just that those are, for example, smaller solar masses. This is much, much higher solar mass. So people, scientists seem to believe now that the large GRBs are due to hypernova. This by itself is a very fascinating field. It's a big puzzle for quite some time. It has solved only in the last few years. Okay, and these are all, as we know, very extragalactic phenomena. Okay, and as I said, because it is already I noticed that it was done, so I'm not going to skip that part. Now I come back now. We have done the low energy gamma ray astronomy. Now we will try to do the medium energy gamma ray astronomy. And what we said at that time is the Cherenkov radiation is what becomes important. Now these are the two things which you please look at it. The left hand is what is the extensivation takes place, a cosmic ray or a gamma ray or anything comes and makes lots of particles, and they give out Cherenkov radiation. And what is Cherenkov radiation? We already talked about a lot. So I'm just putting the two together so that you understand, and that the particles have to have some they are relativistic particles. So now what we do is we try to look at the Cherenkov radiation, and let us see. This is okay. Now what happens is the gamma ray comes, and gamma ray, what happens first? So-called pair production, but then slowly lots of particles come out. This is how, for example, the particles look. But the particles themselves are not important at these energies. They may even die down. But what happens is this Cherenkov radiation. You can see it is essentially like a football field. It will be spread over that, and the very interesting aspect of this is it's a flash. That is what is very different. For example, there is night sky, all types of things are there, stars, etc., etc. But this is our only phenomena we know which happens in a flash. It's a blue light flash, and so this happens as in both cosmic rays and gamma rays do. Cosmic rays in this field is actually noise, and it's isotropic, whereas the gamma rays will only come from one direction. That's the thing you are going to be looking at it. So if you find your directions very accurately, you can say that this Jericho radiation is due to gamma ray. You can see the type of detector. I'll go more deep into it, but this is what it is shown. It's a kind of an optical telescope. Now, if you, as I said, now if you, for example, if you put a mirror in the backyard or somewhere, and then you go and looking at the light for somehow, this is actually a photomultiplier, looks at it. What happens is the low level light is all due to night sky background, that is due to the stars, etc. But the very high ones are due to Cherenkov light. Okay, now this is how it is shown in this particular plot, and this is essentially a mirror looking up at a photomultiplier catching whatever light it sees. So this particular type of technique is called atmospheric Cherenkov technique, and because we again look at light, the light, so it is, has to be done. It's a weak light, clear moonless night, just like good optical astronomy. And the duty cycles are less because obviously it's a nighttime experiment. And as I told you, the light pool is very big, 200 meters or something like that at Hadley altitudes. And it's a blue light, we have already discussed that. And so what we do is, here with the techniques of so-called high energy physics and cosmic rays come, we put several detectors and we take what is called a coincidence, fast coincidence between several mirrors or telescopes to minimize night sky, because we know what night sky is a nuisance here. So this is again like an optical telescope's limited field of view, so it will be tracking. So this is the type of experiment we are going to be doing, and I'll just go a little deeper into it. And in India, these experiments started quite early. These are called the what typically first generation instruments, and it was there in Ooty. I already talked about Ooty, and also in Gulbarg. The top one is Ooty, the lower this thing is Gulbarg because it's snow there. But later, this is done by the TIFR group and then the BRC group. These are the two groups which do this work. And this is in Mount Abu. It's called a tactic experiment. Let me see whether I think there's something more. Yeah, this is called Pachmari. This is in Madhya Pradesh, near about 2 kilometers from Bhopal. And this is the so-called Pachmari array. This is the Mount Abu BRC array. So these are the typical experiments which are done. And they're kind of now, they are kind of fading because now, as I'll discuss now, we have come to another generation of Cherenkov detectors. So here one uses two different techniques. Let's not dwell too much on that. Essentially, it depends on whether you're going to have a very huge dish. This is a 10-meter dish, diameter, and you put a lot of photomultipliers. Photomultipliers, as you know now by now, light sensing devices, or you spread out. Okay, this is for example in Pachmari, the left one. This is in Arizona in Whipple, but we will see in India also we'll be doing something like that. Now, I want to talk about 2-3 results of this field because these are very important. And again, we come back to CRAB, which never leaves us. Okay, CRAB is such a standard source, and it has been shown to see to emit these very high energy gamma rays. By very high energy, what do I mean now? At this stage, I mean about few hundred GeV, about 500 GeV. Now, I won't go into deep into the actual graphs, etc. here, just to show that it's what's called a standard candle, because if you do it for 10 minutes, you get so much. If you do it for 20 minutes, you get double like that. Okay, and so that is what this CRAB nebula has to be done, because it's like a calibrator. Okay, and now this is shift and skip. But here is one thing which I would like to show, that you see, even a very modern, very new field like the gamma ray astronomy can shed light on old problems. Here, for example, this is an energy spectrum from CRAB, and here are the points. Now, theorists go ahead and see what type of magnetic field is necessary, and they found that, for example, 16 Tesla. Now, the magnetic field in CRAB was not known, but because of this, now it is known. This is what I want to stress.